Hi, welcome to another lecture on Calculus 2. Today we are going to continue our conversation about infinite series, and we are going to look at two other methods for determining convergence, and these are called the ratio and the root test. Let's go ahead, take a look at this quick and interesting topic. So ratio and root tests are a test for convergence of a series. We have looked at quite a few ways of determining convergence or divergence, and here are two other new methods for the same task. To understand them, it's a good idea to go back to the geometric series we had a couple of lectures ago. What was the character of geometric series? You start at a certain number, and the next term is obtained by multiplying the previous one with a certain number, and the next term obtained again in the same way. So every time you are multiplying by the same factor r. So this was the shorthand way of writing this: a times r to the power of n ranging from 0 to infinity. We said this is a particularly simple series. Its sum can be determined is the first term divided by 1 minus that multiplying factor, provided that that multiplying factor is less than 1. So that's the condition for convergence of the geometric series. This is the crucial thing that's connect to what we have in mind right now. Well, for geometric series, how can we tell what the multiplying factor is? Let's go ahead and write a simple example so that we can have a sense for this thing. Suppose I have a series nicely starting at 1/2, and every time again we are multiplying by 1/2. So the next term is 1/2 squared, next one is 1/2 cubed, and so on. Or if you want to expand it, it's 1/2 and 1/4 and 1/8 and 1/16 and etc. Okay, when I look at this series, how can I extract that r? Well, first of all, why do I want to extract the r? Because that's what's going to tell me if the series converges or not. So in this case, how can I extract r? So one way, here we were multiplying by r to get the next term. If we divide consecutive terms, we are going to see what the r is. For example, if I take 1/4 and divide it by 1/2, so the next divided by the previous, or if you wish 1/8 and I divide by 1/4, or if you like 1/16 divided by 1/8, in all of these cases the ratio is 1/2, and since 1/2 is less than 1, I know for sure that the series is going to converge. There is another way of catching r, and that's by taking root. Of course, if I take the first root of 1/2, or if I take the second root of 1/2 squared, or if I take cube root of 1/2 cubed, in all of these cases I get the same factor 1/2. So this one, the first one, perhaps very unfamiliar. It just means you take in the number as it is, you're not doing anything to it. This is your ordinary square root, ordinary cube root, and so on, and all of them are equal to each other, and it's 1/2. It's same as this number. So in both of these cases the ratio is 1, and therefore I know that my series converges. Now the ratio and root test are based on a similar idea, that if I take a ratio of two consecutive terms of a series, or if I take the nth root of the nth term of the series, and the resulting number is staying below 1, then my series is going to be converging. If those ratios tend to be larger than 1, then the series is going to diverge. If the ratio is exactly 1 at the limit, we are going to be facing a complicated situation, and we have to go after so-called plan B to determine convergence by some other means. Let's go ahead and see how we are going to apply this idea. So the general idea we have is that the ratio and root test are applicable to series that are useful for a series that are built on top of multiplication or power. So what does that mean? You see that here I have powers in terms of the series, kind of obvious. Or if you wish, instead of a power, you can think about multiplying to create the nth term of the series. If you are creating your series in such a style, it's likely that these two methods are going to be applicable. So I've here written a couple of series for you to see. For example, here we are having powers built into terms of the series. When you have factorial, it means repeated multiplication. That is again a signal that perhaps ratio and root test are going to be useful for us. So the idea that we have is the following. If so what we are going to say is that if I take ratio of two consecutive terms of the series and that ratio stays below 1, let's make it more specific. If I have a series, I write the series as a sub n. I'm going to take consecutive terms. So consecutive would mean, for example, an plus 1 to an. If you wish, you can write an or an to an minus 1. Okay, so this is the next term, that is the previous term. If the limit of this ratio as n goes to infinity exists and it is less than 1. Now, to make the matter simpler, we just take the absolute value and ask that this limit is less than 1. If that is so, then my original series is going to converge. So let me write it like this. So if limit of the ratio of consecutive terms is less than 1, then the series converges. Essentially what happens is that we are going to compare it against the geometric series. By comparison test, we see that it converges. On the other hand, if I notice that the limit of a ratio of consecutive terms is some number larger than 1, it's every time I go from one term to the next term, I'm multiplying by something larger than 1 at the tail of the sequence. That's what I'm doing. Then for sure I know that the series is going to diverge. Like what? So for example, if I had 2 plus 2 squared plus 2 cubed and so on, you know immediately that this thing is going to diverge, because of course you're adding bigger and bigger terms to it. There's no way that it's going to settle down for anything. But if you are multiplying by 1/2, you have convergence. Now what if the limit is exactly 1? Well, that's when we are unlucky that our ratio test is not going to be successful in determining anything. We cannot say one way or another as to what's going to happen. So if the limit of an plus 1 to an is exactly 1 when n goes to infinity, then the test fails. Ratio test fails, meaning we are not clearly in this region or that region. We don't know. Based on this test, we cannot have a verdict. We have to go to something more powerful to figure out what is the case. Now, if this ratio turns out to be infinity, that's obviously this larger than 1, and the series we say it diverges. Okay, the proof is simple. So let's go ahead and just practice a few examples here. So suppose I have show using ratio test that sum of let's write something like say 5 to the power of n over n factorial converges, or test it and decide if it converges or not. Okay, so here I say my nth term is what you see here is 5 to the power of n over n factorial. Who is going to come after that? That's a sub n plus 1. That means our exponent going up one notch. This factorial also going to go to the next factorial, whatever it is. The ratio of these two, we might as well calculate it and simplify before we actually apply the limit to it. So I'm going to have an plus 1, which was 5n plus 1 over n plus 1 factorial, and then divided by 5 to the power of n over n factorial. Of course, for dividing fractions, you remember you flip and multiply. So this is going to become n factorial and then 5 to the power of n. Okay, the trick always is in simplifying these things. These two powers you can simplify, and let me ask you to simplify that and come back in a second and tell me what is that ratio. So you want to pause this problem and find the ratio, and then come back and tell me what the limit of that ratio is going to be. Of course, well, the ratio of these two is going to be 5. That's the easier one. Perhaps the one that you require a little bit more practice with this thing. What is n factorial over n plus 1 factorial? So let's remember, n factorial means product of all numbers up to n. And n plus 1 factorial, well, you go all the way to n, and then you have one more term, n plus 1. So if you take a ratio of these two, this part is going to cancel out, and all we are left with is n plus 1. So this is the ratio. Now what is the limit of that ratio? What's the limit of an plus 1 over an? In this case, if I take an absolute value, it doesn't make any difference. So this is the limit of, same thing, 5 over n plus 1. N goes to infinity. What is the deal when n goes to infinity? Well, when n goes to infinity, this ratio is what? It's of course 0. And 0, definitely less than 1. That's the strongest result you could have. If the ratio turns out to be 0, it means it converges quickly. So since the ratio is 0, we conclude that the series converges. Okay, so we know that the series converges in this case. Now let's go ahead and take a look at a different example. Does series, let's write n squared 3 to the power of n 5 to the power of n converge or diverge, and do so by ratio test. Well, so we learned the idea. we write the formulas for two consecutive elements of series, take a ratio, simplify, take a limit of that. If the limit is less than 1, the series is going to be converging. If it is more than 1, it is going to be diverging. And if it is right at between, well, this test is not a suitable test, and you cannot kind of figure out one way or another as to based on this test, you cannot figure it out. So what we write is the n term, and the next one, so that's going to be n plus 1 squared, 3 to power of n plus 1 over 5 to power of n plus 1. The ratio of these two, let's write this, and let me ask you to pause this thing and quickly figure out what that ratio is. After you do a few of these things, you should be able to clean this up quickly. So let me continue down here. So an plus 1 to an is, let's write similar terms next to each other so simplification becomes simple for us. So I have 3n plus 1 over 3 to power of n, and then 5 to power of n over 5 to power of n plus 1. So make sure you don't make a mistake as to where does everybody go. Okay, these powers are easy to simplify. This simply becomes 3, this simply becomes 5. So now I have n plus 1 squared over n squared, and here I have 3 and here I have a 5. Well, what's the ratio of these two going to do? Well, as n goes to infinity, what happens to this portion? Let's just play with this thing. So n is, say, 10, but that's going to be 11 squared over 10 squared. That's almost 1.2. Say n is 100, that's going to be 101 squared, and this 100 squared. As n goes to infinity, this portion goes to 1, this portion goes to 3/5, and the ratio becomes closer and closer to 3/5. To see that, let's go ahead and open this thing. So I write this thing n squared 2n plus 1 over n squared, then times 3/5. Let's go ahead and simplify this thing by dividing by n squared. This is 1 plus 2 over n plus 1 over n squared times 3/5. So if I want to take a ratio of two consecutive terms, I'm taking the ratio of this. It's a limit of 1 plus 2 over n plus 1 over n squared times 3/5 as n goes to infinity. Well, this term and this term go to 0. I have 1 times 3/5, and that is 3/5. Again, I forgot to put the absolute value here, but everybody was I need to put the absolute value here, but it's the same thing. So this ratio is less than 1, and as a result I can say the original series, which was n squared 3 to n 5 to n, this one converges. Okay, so we have seen a couple of cases where the series is going to converge because what we had was a ratio that was less than 1. Let's try another one. Suppose I take the series just 1 over n. Test series sum of 1 over n for convergence using ratio test. Well, there we don't see much of a multiplication here, so ratio test is not such a great idea for this kind of situation, but let's see what happens. So I have an is 1 over n, an plus 1. Next element is going to be 1 over n plus 1. The ratio of these two is we clean up, it becomes n over n plus 1. We can divide numerator and denominator by n to get it into the following term. Well, what's the limit of that? The limit of 1 over 1 plus 1 over n, that's the limit of an plus 1 over an. Well, when n goes to 0, n goes to infinity, this ratio goes to 0, this becomes 1. And we said when the ratio becomes 1, the test fails. Fails means we cannot decide, is it this or is it that. This test doesn't tell us which it might be, so the conclusion is just that the test fails. We don't have anything to say about original series. Almost feels like having wasted time. So, well, we had done integral test before. By integral test, we know this thing diverges because the integral of 1 over x, that is logarithm of x, and that one diverges. I know this one diverge, but this test doesn't tell me that. It just fails to say anything. Similarly, if I have minus 1 to power of n over n, if the question is test this one, then again an plus 1 over an, just like this, it's 1 over 1 plus 1 over n, and that one also tends to 1. So again, test fails. The test fails. But what do we know for convergence of this? Do we know it converges or diverges? Yeah, well, you saw it in the previous lecture. This is, of course, alternating series. The terms are declining towards 0, and of course it converges. So, the ratio test is mute in both cases, but however we know from somewhere else, okay, some other test, that the first of these things actually was convergent. It's just that the ratio test doesn't tell us. Excuse me, I wrote it opposite. 1 over n diverges, and if you alternate it, it does converge. So last time we said it's called conditional convergence now. So we know that what the result is from other tests. It's just that this one doesn't tell us any of that. Okay, let's go ahead. So that was a style 1. Style number 2 is root test. So what's the idea of a root test? Idea of root test going back to geometric series. If the root of the nth term tends to be less than 1, then we have established convergence. But opposite case here, if the nth root of nth term is larger than 1, then it's going to diverge. So what is suitable for this case? Usually the series that are built on top of powers, variable powers, are going to be the easiest problems in this case for this type of a test. So let's take a look at some example. Test. So let me first write the statement. The series sigma of an converges if the limit of nth root of its nth term as n goes to infinity is less than 1. We will know it diverges if same limit becomes larger than 1. And again, test fails. What do you think? When does the test fail? Well, you have learned by now. If this becomes exactly 1, then it's our unlucky day. We don't get anything out of our testing. We have to go find some other way of handling this issue. Okay, what would be the simplest of this? Let's do an extremely simple case. Test Okay, very simple case. Sum of exponential of minus n. We want to test it for convergence using root test. So what is the idea here? You look at the nth term, then you look at the next one, so instead of n I have to write n plus 1, and to be careful we have to put it in the parentheses. We take the ratio, and the ratio is exponential of minus n plus 1 over exponential of minus n. Well, one way to simplify this is to say it's the same base, and I'm going to subtract the exponent. So this is the exponent of numerator, this is the exponent of denominator. When I subtract them, I get what? N's cancel, and I have just minus 1 left. What is exponential of minus 1? Same as 1 over e. Well, e, if you remember, e is 2.71, etc. Reciprocal of that obviously is less than 1. Well, the ratio is a fixed number, so if you take a limit of it, you get the same thing. Limit of exponential of a n plus sorry, I have to backtrack. Let me finish this thing. I said let's do a root test, but here is by mistake I started with the ratio test. Let me finish that up. So by ratio test, this is so by ratio test it converges, but my mistake, we were supposed to do a root test, not a ratio test. Root test. So an is exponential of minus n. I want to calculate nth root of an. So that is the nth root of exponential of minus n. How do you handle this? Well, one way to do that is to divide this exponent by that exponent, exponential of minus n over n. So that is exponential of minus 1, just like that one. So the ratio, or the limit of nth root of an as n goes to infinity is just going to be the limit of, it turns out to be a constant number, so that's just exponential of minus 1 or 1 over e, which is less than 1. So as a result, we can say that the series converges. Okay, so maybe I better do another example of this thing so that uh, consider, say, n over 3n plus 1 to power of n. Use root test to determine convergence. Well, the problem telling us what test to use, so that makes it easy. I have the n term to be the following. What is nth root of this? Now in reality I have to take absolute value, but here everything is positive. There is no nothing gained by taking the absolute value. But anyway, if I take the nth root of n power, I just get the item in the base, so that's going to be n over 3n plus 1. So in this case we had it really easy. When we take the nth root of nth term, I get this one. And so now if I ask what's the limit of this as n goes to infinity, it means I'm taking the limit of this fraction as n goes to infinity. Well, this is something you see in pre-calculus and such. The ratio is 1/3. As a result, we can say what? As a result, we can say the series converges. Let's do another one. Okay, now we have an. Everything is positive here. Well, n to power of 2 you can multiply old and new exponents, becomes n to power of 2n. The nth root of an, well, let's write it. The nth root of n factorial to power of n, and then n to power of 2n. Let me write a simple rule here. If you have a to power of p, let's write it b to power of q. This is a to power of p over n divided by b to power of q over n. Is that right? So n becomes the denominator of these exponents that you have there. So that's from your algebra. So here we have n factorial to, it was originally to power of n, then you're taking the root n, and then denominator you have n to the power of 2n, and then you're taking the ratio n. So numerator is n factorial, denominator is n squared. So the ratio becomes this. Now where does this ratio go? N factorial over n squared. As n gets larger and larger, you see that here you're just multiplying n by n. Here you're multiplying all the numbers from 1 to n. So which one do you think is going to be bigger? Obviously, numerator turns out to be much bigger than the denominator. So as we take the limit of nth root of an, factorial grows substantially faster than any polynomial, and the ratio goes to infinity. If the ratio goes to infinity, what can I say? We said if the ratio is actually larger than 1, the series is going to diverge, and this is going to be almost the worst divergence that you can have. So in this case, we say the series diverges because the limit becomes infinity. Okay, many problems in this case are resolved by one of these two series tests, and if the test is inconclusive, sometimes you might be asked to apply some other test and figure out if your series converges or diverges. Okay, so we are going to apply the methods that we have learned to studying generalization of polynomials. These are going to be called Taylor polynomials, and more advanced topics coming up. Until then, good luck and God bless.